Hello? Yeah, okay. Okay, hello everyone. My name is Yifan, and this talk is about fast atomicity monitoring. So concurrency is everywhere for the modern software system, and concurrency bugs are also everywhere. According to a survey published on ASPLOS, about 65% of non-deadlock bugs of a concurrent program is atomicity violation. So here is a real example of atomicity violation in Masoko, and it has resurfaced for several times in the history. So basically, there are two different threads in this concurrent program. The thread one, both of the two threads, they actually try to access the field proc info. But the issue is that developers assume the statement S1 and S3 are executed automatically. But the issue is that the statement 2 in the thread T2 can be interleaved with S1 and S3. And this will cause a non-pointer dereference, which will crash the database. So atomicity may not be respected due to program's error. So how do we detect atomicity violations? We can use static analysis by scanning the source code of the program and just report if there's any violation in the source code. But the issue is that it has a lot of false positive. For a concurrent program, false positive is really hard to verify and can be a huge waste of time. So the most popular method for detecting concurrency error is actually dynamic analysis. For the dynamic analysis, the checker will observe the execution generated by the program, and it will check if the observed execution violates the atomicity. So here is a trace generated by the concurrent program. A trace sigma is actually a sequence of events in a total order. We call that trace order. A transaction, it is a sequence of events in thread T, and it begins and ends with the small triangles. For example, here, the transaction T1, it actually have 2 events. And each transaction can be considered as an atomic block. We say that 2 events, E1 and E2, are conflict if they are in the same thread or they try to access the same variable X, and at least one of them is a write event. Or in another case, they try to acquire or release the same lock. So in this example, the event E3 and E4, which read and write on the variable X, are a pair of conflict events. So for the 2 events E1 and E2, we say that E1 conflict happens before E2 if first they are conflict events, and E1 appears before E2 in the trace. We use the arrow to represent the conflict happens before partial order. So a trace, it is serial if all events in transaction T are executed without interleaving with other transactions. So if we look into the first 2 traces, we can see that the transaction T1 and T2 are not interleaved with each other. But for the last trace, T1 overlaps with T2, so it is not a serial trace. A trace may not be serial, but it can behave as it is a serial trace. So we say that a trace is conflict serializable if we can reschedule the events of the trace to get a serial trace sigma prime, and the conflict happens before partial order remain the same to the original trace. So here is an example. The first trace, sigma 1, it is not a serial trace because you can see that the transaction T1, it overlaps with all the other transactions. But we can permutate the events and transactions to make sigma 1 into a serial trace sigma 2. And all the conflict happens before partial order remain the same. So sigma 1, it is conflict serializable. If a trace it is conflict serializable, it means that there's no atomicity violation. So the problem is how to check if a trace sigma it is conflict serializable efficiently. To introduce the algorithm, we have to define the transaction happens before partial order. Given two events, E1 and E2, if E1 conflict happens before E2, then we say that the corresponding two transactions have the transactional happens before partial order. So if we look into the example, the E3 CHB E4, so the transaction T1 happens before transactional happens before the transaction T2. And if a trace is not conflict serializable, it means that the transactional happens before partial order. It is irreflexive. The first paper trying to solve this problem is the Aerodrome algorithm. And the idea is very trivial, actually. So it maintains a graph to represent the transactional happens before partial order. All the vertices correspond to transactions, and the edges represent the THB partial order. So if there are a pair of conflict events, and for example, in this example, E3 conflict happens before E4, so we just draw an edge from the transaction T1 to transaction T2. And similarly, because of the events E5 and E6, we draw an THB edge from T2 to T1. If there's a cycle in this conflict graph, then we say that this trace it is not conflict serializable. So the time complexity of this algorithm is n squared. It is very high because in practice n is very large, and n here it is the number of events in the trace. There are also several other papers trying to resolve this problem, and our algorithm is actually the fastest one. The time complexity is nk squared. Here n is way smaller than k is way smaller than the NVL. K is the number of thread, and NVL corresponds to the number of events, locations, and locks. We have to mention that the consumption of memory footprint is also very small, so that we can implement our algorithm in an online tool because of the very low overhead of time and space complexity. The key idea of this algorithm is that we maintain two data structure, which is called latest remote transaction and earliest local transaction. The latest remote transaction is, for example, the LRT T2, T3. It represents the latest transaction in T3 that can reach the transaction in T2. So here, the LRT T2, T3, it is the transaction T1 because it has an outgoing edge from T1 to the transaction T3 in the thread T2. The earliest local transaction is the earliest transaction in T2 that is reachable from the LRT. So in this example, the earliest transaction in T2, it is actually T3 because it's the first transaction reachable from the LRT, which is T1. The key lemma of our algorithm is that given two conflict events, E1 and E2 in two different threads, there are three conditions to detect a violation. So intuitively, the first condition will capture the THB edge from the thread T1 to T2, and the second and third condition will capture the THB edge from thread T2 to T1. So if all the three conditions are satisfied, it means that there's a cycle in the graph. So here's an example to illustrate how our algorithm works. The event E13 is a CHB immediate predecessor of E14. So the two events are actually the last two events in the trace. And the LRT T2, T3 is the transaction T1. The ERT T2, T3 is the transaction T3. And it appears before the transaction T5. So all the three conditions are satisfied, then a violation is detected, which is the cycle from T1, go through T3, T5, then back to T1. Our algorithm is based on lemma 2, and we find that recording LRT and ERT is very difficult. So we can maintain them approximately. We can update two vector clock from and to in the complexity of k square. We make sure that when the LRT is open, we always have the vector clock from equal to the LRT. And this should be sufficient for lemma 2 to find a atomicity violation. So the time complexity of the whole program is nk squared. So for the experiment, we implemented our algorithm in two frameworks. The first one is the offline framework for dynamic analysis in Java program. And we also implemented an online version in thread sanitizer. For the offline experiment, we compared our algorithm with all the other existing tools. And the result shows that our algorithm is actually way faster than the existing tool. For the online experiment, we actually adapt the instrumentation framework of thread sanitizer. Here, the data of T-SAN, it's actually the time consumption for the data race detection algorithm. And for our algorithm, you can see that the time overhead is actually very small. It's only 1.3 times slower than thread sanitizer. For the memory overhead, it's actually can be omitted. Yeah. So the conclusion is that Atom sanitizer is faster than the other tools, and it has smaller memory footprint. It is the first online tool implemented in thread sanitizer to detect the atomicity violation. And the experimental result confirmed the practical impact. Yeah, thanks.
We have time for questions.
So probably a naive question. Why is it that transaction serializability is equivalent to no atomicity violation?
Yeah, it's actually a lemma borrowed from previous paper.
Oh, okay.
Yeah.
So it's not an immediate thing?
Yeah.
No, I don't think that's what he asked. He's not contesting the lemma. He's saying atomicity violation and conflict serializability, they may not be the same.
Sorry? Yeah.
There's a slide where, like before you get into the techniques, you said that atomicity violation is equal to serializability. Yeah, this one. The first statement.
That is true.
Yeah. So here I think it's the atomicity violation is by definition based on the conflict serializable.
So this is an implication.
Yeah.
Conflict serializability implies
Okay.
Yeah. So it's actually just an abstract property of all the transactional system.
So you would be given the trace, but you don't execute it. You first serialize it, and then you guarantee there's no atomicity violation.
I think we could take this offline. But yeah, I mean, you may be confused by the equals, but I think it was error. It's an implication, yeah. Any other questions? I had a question. I was curious what is like the largest code this is scaled to in terms of number of threads, in terms of lines. It's unclear, at least from the talk.
Yeah. We illustrated that in the paper, around like 50 gigabytes of the traces in binary format. So it can be really huge. Yeah. Yeah, fixed point.
Number of threads, this kind of things. How many threads can you support?
The number of threads we can support, actually there's no exact upper bound, I think.
Yeah.
Yeah.
How does it scale?
Yeah.
So basically, how does it scale with a large number of threads? Like, how about traces with 56 threads versus traces with only 8 threads? Are they the same in your algorithm, or is the 56 threads traces much harder to process? This is a question.
Yeah, actually, we also tried to conduct the scalability experiment. We find that because the 56 goes to 128, it's actually a small number, so it doesn't change the performance that much.
Okay, I
yeah.
see.
Let's thank our speakers, and now we have a break.